Hello, everyone. As Dr. Salami said, my name is Mitch Thiel from Bradley University, and I'm an undergraduate research assistant. And I'm going to be presenting my research on flexural behavior of bamboo reinforced sulfur concrete beams for planetary applications, which I'll get more into in the next slide. So the overall agenda we have for us today is what is the Martian mission? So what was our goal going into this? And details about sulfur concrete, which we don't use regular concrete in this experiment. And we're going to use bamboo to use it as reinforcement. I'll go into details about why bamboo and sulfur material properties, the test variables and the test matrix, and the results and conclusions. So let's begin. What was our goal going into this project? So we are funded by the Illinois Space Grant, which is under the direction of NASA. So our research is to look into settlement on Mars, which is the next huge leap for humankind, which is what NASA's goal is coming up in the next coming years. But the challenges that come with that is transporting building materials from Earth to Mars, because it has high cost and we don't want to spend too much money on materials. So our goal is looking at using indigenous materials found on Mars itself, which includes the Martian soil and sulfur, which is readily available on the planet itself. And bamboo is what we're focusing on in this particular research. So let me get into the details of what the sulfur concrete is made of. In the first picture on the left, you'll see up there is Martian soil, which is approved by NASA. They will have taken soil from Mars itself and then replicate it here on Earth for use in experiments, so that we don't have to constantly keep going back there to get testing materials. So that's approved. And then in the middle there, we got solid sulfur, which is just sulfur itself. And then the goal of this is different than regular concrete. We actually have to melt the sulfur down to its liquid component and combine it with the Martian soil, unlike regular concrete. So in this case, we're using 50% Martian soil by volume to 50% sulfur by volume. So depending on the mold, which you'll see in the far right picture is a 2-inch by 2-inch by 10-inch mold. So we are taking enough volume, but with ratio 50 to 50 to fill that mold. And once you get that volume, you combine it in one bowl, kind of mix it up a little bit so it's more evenly spread, and then you put this bowl and the specimen mold right there into the oven at the same time at 150 degrees Celsius, which is the melting point of sulfur. It takes around, depending how much soil you have, 35 minutes to an hour and a half, but periodically you'll go throughout the oven and mix it up so it kind of helps with it to melt faster. And then after the time's up, you'll notice it's like all one consistent color, kind of like you're baking a cake. And then once that's ready to go, you'll take the mold out, put it onto a shaker table, then take the bowl with the freshly melted sulfur and Martian soil combined, mix it before you pour it, and pour it into the mold on the shaker table while it's running low to medium. You don't want it too high. The shaker table is essentially to make sure that when the liquid is poured into the mold, it settles and it's not like having little air gaps in there. So once that's done, you move the mold, and then within 24 hours, you could take it out of the mold. It hardens very quickly, so time is of essence when you're pouring it. It takes 24 hours to reach 90% of its full structural capacity, which is way quicker than concrete, which is usually 28 days. And on the right, you'll see a typical specimen. That's a 2-inch by 2-inch by 10-inch beam of sulfur concrete. This one on the left, you'll see has actually one bamboo, but we'll go more into that in the later slides. And on the right, you'll see a 2-inch by 2-inch cube. So the whole point of this research was we're going to structurally reinforce this sulfur concrete member with bamboo instead of steel, which is normally used for reinforced concrete. So why did we choose bamboo? Well, first of all, bamboo is a relatively high tensile strength, and you can see around the world they are using bamboo for some applications for construction. So we are taking that and implementing into more planetary applications on Mars. And overall, bamboo has a lower unit weight, which results in reduced transportation costs, which is a huge focus of the Martian mission, is having a lower cost of transporting our materials to Mars, which we would rather bring other things up there besides our building materials. So bamboo is a prime candidate for that. And also, the bamboo has the ability to grow on Mars itself. So once you bring it up there the first trip, you will never have to bring it up there again, which is essential for bringing other things up there, which is why we focus on the bamboo aspect of it instead of steel, because steel as to our knowledge, is not found on Mars. And then this is just this test setup of testing the tensile strength of the bamboo. As you can see in the far right picture, it has a brittle failure into it, unlike steel, which kind of bends. And then here's more bamboo properties we're going to talk about. On the right, we have a strain versus stress graph. As you can see, it reaches out kind of a linear line up to 22 KSI, where then it falls straight down, which means it has a brittle failure, which was expected. And on the left, you'll see our table where bamboo has an overall tensile strength of 22, which can be seen in the graph, a modular elasticity of 1064 KSI, and an overall density around 46.5 pounds per feet cubed. And then we're comparing this to A336 steel in this case, which has around 36 KSI tensile strength, 29,000 KSI for modular elasticity, and 490 pounds per feet cubed, which is all pretty well known. And on the right-hand side of this table, we have the ratio between bamboo to sulfur. So for tensile strength, 61%, modular elasticity 3.7%, and density around 9.5%. It's important to note that even though that bamboo is 61% that of steel for the tensile strength, it is only 9.5% the density of overall steel, which is essential when, as we're going back to this goal again, transport materials to Mars is expensive. So the fact that we're getting 61% that strength of steel for 9.5% density is huge for future applications. In our next slide, we have just material properties of plain sulfur concrete without any bamboo. So for using 3 specimens, we tested our 2-inch by 2-inch by 2-inch cubes, and we're getting a range from 5.1 to 6 KSI for overall compressive strength, which is an average of 5.5 KSI, which is pretty large, including that there is no additives into the sulfur concrete mix. It's just sulfur and the Martian soil, which is 5.5 is the low, which is pretty good. And then here we have the tensile strength for sulfur concrete, which is a range of 0.75 to 0.81 KSI, average of 0.78 KSI. So we're expecting around 10% of normal concrete compression strength for its tensile strength. But in this case, our sulfur concrete was reaching around 15% its tensile strength. This is just for sulfur concrete by itself. Just throwing out some little facts about it. All of these were calculated using the Flexural test. And here's our test setup, pretty typical. We have a 3-point bending testing with a slow loading load onto the specimen itself. And then here we have the nomenclature of our test species. So you'll see SC stands for our sulfur concrete, and then the B stands for the bamboo. Where it starts changing is the first number, which is the number of bamboo. In this specific case, we did 0, 1, and 2. And then the last number indicates what specimen number that is for that specific bamboo, 1, 2, or 3. An example bomb is SCB03, which means it's 0 bamboo, but it's the 3rd replicate of that. And here's our test variables. As you can see, all specimen sizes were 2-inch by 2-inch by 10-inch. That did not change. The thing we did change, which was important, is our bamboo number, which is 0, 1, and 2. The bamboo area, and for all of these, we were not focused on the sulfur percentage compared to Martian soil, so they're all stuck with 50, and then replicates 3. So we have some tested pictures already shown. This is a tested specimen with 0 bamboo, and as expected, has a brittle failure. Not much else to show from that one. The next one, we actually go into a 1 bamboo. As you can see, still a brittle failure. As you can see in the right picture, the bamboo just snapped, which is what was expected at the time. But as you go to 2 bamboo, as you can tell, the specimen itself, it did crack, but it did not go fully through the bamboo, which is like a good finding, and which just shows as you add more bamboo, the ductility will increase in the specimens. So what did we find? So our experimental moment is on the left side, and then our specimen names are right there. We had an average around 1,100 pounds per inch for just regular sulfur concrete, but as you increase to 1 bamboo, the experimental moment did increase by around 50% to around 1,600 around there, which is a big jump. And then from one bamboo to two bamboo reached a 25% increase from 1600 to around 2100. And then for we have a specimen name on the lower axis in the experimental moment for nominal moment. As we start with, we're only focusing on the one bamboo and two bamboo because this research is focused on, is bamboo a good reinforcement for sulfur concrete for planetary applications? So we didn't account for the zero bamboo, but when we got one bamboo, we had an average around 0.85, which means it's not as conservative. But as you can see, as you increase the bamboo, we do jump to a 1.35, which means as you add more bamboo to the sulfur concrete specimens, you will become more conservative, which is what we wanted. And this could be due to the fact that when you make the sulfur concrete like better, I guess you could say in quotes, you have to pour it into the specimen. So as you increase the bamboo, there's more area for the sulfur concrete to bind to. So as you add more bamboo, it creates a stronger, tighter bond to this bamboo itself. So that's why we're seeing an increase in this. So what can we get from all of this? Bamboo has the potential to be planted on Mars, which is huge for NASA's goal of lowering their costs. Once we get it up there, we're done. Like they don't have to worry about costing that in their whole application. The tensile strength of bamboo is 61.1%, that of mild steel, which is huge when the density of bamboo is only 9.5% of that of mild steel, which I want to drive in there, lowers cost down, which in most days cost is very essential. And the flexure strength of sulfur concrete with one reinforced bamboo showed approximately 50% higher compared to no bamboo, sorry. So as you go from no bamboo to one bamboo, you'll see a 50% increase in that flexural strength, which is showing that this bamboo is actually working for the flexural strength. And as we go to one bamboo to two bamboo, that increases as well to 25%, which further proves that the more bamboo you add, the more it's able to withstand. And then our final conclusion was the average nominal flexural strength of sulfur concrete from one bamboo is around 0.85, which means it's not that conservative, but as you increase it to two, it jumps to 1.35, which makes it more conservative, which essentially shows by adding more bamboo, there's a stronger bond within the specimen itself, and it leads to a higher flexural strength, which overall proves that as you add more bamboo, it works better for the sulfur concrete. I just wanted to say thank you to ACI for allowing an undergraduate student to present, and if anyone has any questions, I would love to answer.